continuation of the previous class on chemical properties of haloalkanes. The reactions are nucleophilic substitution of haloalkanes by strong nucleophile. The strong nucleophiles, the examples I have taken as OH minus, Cn minus, cyanide, and NO2 minus, nitrite, and OR minus, that is OH. Here OH minus, H is replaced by organic group, OR minus, it is even stronger nucleophile. And NH3 neutral molecule, ammonia molecule. These are strong nucleophile. So because of strong nucleophile character, these undergoes SN2 mechanism even in presence of protic solvent. As I said, SN2 mechanism is more favorable in aprotic solvent. Because of strong nucleophile character, it can, follow SN2 mechanism even if the solvent is protic solvent like water and alcohol. SN2 mechanism is bimolecular. Both the molecules are involved in a single step of reaction. That is, nucleophile will attack. Nucleophile will attack from the rear or behind this halide. That is halide behind this halide to which it is carbon attack. To this carbon this is attack. So that is from the rear side. So that is what the mechanism involved in SN2 mechanism. Of course, configuration, you get mixture of, that is inversion and rotation. So now look at that some of the examples of chemical reactivity in case of OH minus and Cn minus and NO2 minus and ammonia. What kind of chemical reactivity? The source for hydroxyl ion is sodium hydroxide, potassium hydroxide, and AgOH, silver hydroxide. That is, a moist Ag2O becomes silver hydroxide. Moist means water soluble. So aqueous solution of NaOH, KOH and hydroxyl is a source for strong nucleophile OH minus. If you use any one of them as a reagent, in this case, it is replaced by OH minus, removed as corresponding. If you use NaOH, NaX. If you use KOH, KX, Ag, AgX, replacement. So the chemical examples of, that is methyl chloride, RCl, ethyl bromide, RBr, use the corresponding alcohol and corresponding byproducts. So reaction remains same if you use hydroxyl ion, strong hydroxyl ion, either sodium hydroxide or silver hydroxide. But you take strong nucleophile like Cn minus, so the source is KCN and NaCl, that is alcohol. Protic acid here, protic solvent is alcohol is used. If you use this KCN and NaCl, look at that. If you use this and if you use this, what difference you get? You get RCl, chemical bonding through C of Cl, forming alkyl cyanide. That is structure of cyanide. That is ascent of chain. With this, carbon chain is increased by one carbon atom. That is ascent of chain. If you use this, you get bonding through N, not through C. Look at this. Only Cn only, but that is Cn only, but bonding through N. That is bonding, chemical bonding through N. That is lone pair electrons are there and attacking plus and Cn minus. This is alkyl isocyanide, this is alkyl cyanide difference. So what is the reason for this type of chemical bond? Because here nucleophile remains same, but the molecular structure is different. It is isocyanide, it is cyanide. What is the reason for this? Look at that NC, that is Cn is ambident. What is ambident? After this, no? Ambident means there are two sites for attack, two sites for forming chemical bonds. Two atoms here, the bonding through this C or bonding through this N nucleophile. So either bonding through this C, that is minus is there, already these electrons are taken, ionic, or are bonding through this lone pair of electrons. We call it ambident, two possibilities. It is called ambident nucleophile. Why it is ambident? With KCN or NaCN similar, with AgCN, look at the structure of this. KCN, the chemical bond, here chemical bond, here chemical bond. The chemical bond is ionic. This chemical bond is predominantly ionic. Even the same, it is predominantly ionic. Here predominantly covalent. What is covalent? What is ionic? Difference. You have to go in details about the electronic configuration of potassium, sodium and silver. The electronic configuration of potassium, the outermost electronic configuration I am talking about, that is the one. It is M second shell and last 3s1, third shell and 4s1. After losing electron, forming ion, that is electronic configuration. This electron is transferred to this Cn. Electronic configuration, similar electronic configuration. That is second shell, third shell. Last subshell is P, last subshell is P. That is fulfill, 6 electrons. Subshell, fulfill. Here the subshell last electronic configuration D 5s1. After losing this electron, it may Ag plus. Electronic configuration of Ag plus is this. Last subshell is D, fulfill 10 electrons. So this shell and B cell. Here applies with this P cell, it is noble gas configuration. This also noble gas configuration. This noble gas configuration is called as pseudo-noble gas configuration. What is pseudo-noble gas configuration? The pseudo-noble gas configuration is less stable than that of noble gas configuration. One point. And the second point, here p electrons, the last subshell, the p electrons. The electrons of p subshell has strong shielding effect. But electrons of these subshells, poor shielding effect, very weak shielding effect. What is meant by shielding effect? Shielding effect, the electrons, inner electrons, these electrons, 6 electrons, these electrons have strong shielding effect. These electrons prevent the attraction between the nucleus of the cation and the electron transfer to the anion, there is electron cloud. So it is very strong shielding effect. These electrons will prevent strong shielding, that is 6 electrons. The p electrons will prevent, that is attraction of positive charge, nuclear charge on these electrons. That is why almost ionic separated as what is cation and negative. That is usually there is a character of p subshell electrons. What about the d subshell electrons? Not that kind of shielding effect. The electrons of D shell, poor shielding effect. These electrons, outer electrons, no, poor shielding effect. So those electrons will not, that is, will not prevent the attraction as much as this. So still the attraction of this positive charge on this cloud of electrons, Cn, and causing polarization. After ion formation, it is again polarizing. Pull back the electron, route to this because of poor shielding effect. It is called polarization, induces to it is called covalent character, here ionic character. So among these chemical bond, it is predominantly covalent, it is predominantly ionic. That is why it can dissociate or isolate into as these ions. But this cannot be completely dissociated as into Ag plus and Cn minus. That is the main difference. When the nucleophile attack the carbon of this X, attacking from the right side, now it is isolated. This is stronger. That is stronger is nucleophile than this. That is nucleophile. That is N is there no. The lone pair of electrons are there in this. Lone pair of electrons are nitrogen. Still a lone pair of electrons on the nitrogen. lone pair of electrons. Both sides are available. But when it is this is strong nucleophilic than this. Therefore, this ion is isolated, it can attack this and bonding through Cn, that is alkyl cyanide formation. Just like this. Alkyl cyanide formation. Attack from the side. If you use AgCN, this is not dissociated and isolated as Cn minus. So the whole molecule, see the nucleophile. The whole molecule acts as a nucleophile, but it cannot attack, it is not free, not minus. Still chemical bond is here existing because of polarity. So only site available is this site, lone pair of electrons. Now the nucleophile can attack through this lone pair of electrons, that is oral, AgCN this. And gradually the chemical bond breaks as Ag plus and this. So this is through N. Therefore N is connected now. See no, to the carbon of this. N is connected as like this. N plus and C minus, that is plus and C minus. That is isocyanide bonding through N. So with lone pair of electrons and bonding plus and this is becomes minus afterwards. So that is why we have isocyanide formation or cyanide formation at electron. That is the reason that main reason is the cation difference. If you use AgCN as a reagent, we get isocyanide product. If you use KCN as a reagent, we get cyanide product. The difference. That is chain carbon chain increased by 1 cyanide. So there is a main difference. You get different types of chemical compounds, but same nucleophile. Very important is the one. So we need to understand the property of this chemical bond. It is covalent, predominantly more covalent character than ionic. It is highly ionic character. That is the difference. Here it takes place when I use this. What is that? Example like this. RX C2H5Br. If you use alcoholic KCN and alcoholic AgCN, reagents are different. Same halide. Look at the difference here. Alcoholic, that is cyanide, bonding through C. Here alcohol bonding through N, that is isocyanide. Ethyl isocyanide, ethyl cyanide. Difference is this, reagent difference, but nucleophile remains same. So different compounds get. Example like this. There is a mechanism. Reason for this I explained. Let us move on to the same type of reaction, NO2 minus. If you use KNO2 and if you use AgNO2, what difference you get? Look at the similar type of reaction. That is structure of KNO2, structure of AgNO2, silver nitrite, potassium nitrate. There are chemical bonds in the molecule. Chemical bonds in molecule is lone pair of electrons and nitrogen. This chemical bond is predominantly covalent. This chemical bond is predominantly ionic, same type. Because why it is predominantly ionic? The same reason. Why it is predominantly covalent? It is same reason. Same reason. That is why if you use this, it will dissociate and use what is that free ions like this. This point is more nucleophile than this. This is stronger nucleophile site than this site. Therefore, it can attack. That is, this can attack the carbon from the rare side, forming nitro compound, nitrite, ethyl nitrite. That is alkyl nitrite. If you use generally R. And if you use AgNO2, difference is C2H5. So it will attack the nucleophile of the carbon of this alkyl group through nitrogen, this lone, because still chemical bond is here. This still chemical bond here. So the entire molecule attack this through this N, forming what is that? N plus, and after what is that? Chemical bond breaks, forming as Ag plus. Ag and that is AgBr we get. Here KBr we get. So this is a step, chemical bonding through N. So with bonding, what is the plus formation? This OM minus. This is after chemical bond breakups taking the N minus O minus. is the structure of the compound, that is structure of the product, that is alkyl nitrite, nitroalkane, that is nitro derivative of hydrocarbon, it is a nitrite derivative of hydrocarbon we get. That is alkyl nitrite, nitroalkane, NO2, that is. So that is almost what is that same reason, this is a type of reactions. Difference is cation difference, that is the only difference. Different types of chemical compounds you get product. So now these are the reasons for this, same reason for this. Now another chemical reaction is using OR minus, very strong nucleophile. The source for the strong nucleophile is here RONA, sodium ethoxide, sodium alkoxide. It is organic group, because already organic group is a here or dash. So the source for this sodium alkoxide in dry ether medium, not containing any water, attack on this alkyl halide, what is that? This Na and X forming a byproduct, and this is substituted, that is OR minus, what is substituted to this forming this OR. This is ROR, it is called ether formation, this compound. So this is also called Williamson's ether synthesis. Substitution by OR minus. OR minus replace this X. It is OR minus. It is one. So ether formation. This is also called Williamson's ether synthesis. We are using this chemical equation or reaction for the synthesis of ethers, different types of ethers. Different types of ethers because of the different types of groups you get. This is another reaction. And the last reaction is a reaction with ammonia, RX, and ammonia molecule. Here ammonia molecule. Here ammonia structure is a chemical bond with hydrogen. Because of this RX, that is H and X formation. That is or replace H. And one more molecule here. So one by one, this H plus is replaced. If you add more and more, H is removed by R. That is first H is removed. And one more H is removed by another molecule of this reactant molecule as R. If you use one more molecule like this with the same product, that is with the product, you get this H is also replaced. So this hydrogen of the ammonium is replaced one by the R group of the halide. So it is called as primary amine, just like primary carbon. It is secondary amine, it is tertiary amine. That is amine formation. The attack of strong nucleophile on the alkyl oxide, alkyl halide, use amines, different types of amines, primary amines, secondary amines, tertiary amines. And the compounds, percentage of compounds are different if you take different proportions. If you take more of this, we get almost the tertiary compound. If you take more of this, we get this compound, that is primary compound. But not only is finally, this also can react with one more molecule, forming a compound like this. That is ammonium, that is ammonium like X minus, NH4Cl now. Like this, quaternary ammonium salt formation like this. So this tertiary molecule can react with one more molecule of the halide, forming a salt like this. So these are the reactions with ammonia. And example is, if you use SCH3Cl and ammonia, we get the following mixture. It is a primary amine, secondary amine, tertiary amine, and a quaternary salt like this. That is ammonium, that is tetraethyl ammonium chloride. Here methylamine, dimethylamine, trimethylamine, primary amine, secondary amine, tertiary amine, the reaction between ammonia and methyl chloride. That is the same kind of different. If you use different alkaline, you get different amines you get. So these are the reactions. Very important is the difference. Look at that. If you use nitrite, what kind of product you get? If you use cyanide, what kind of cyanides you get? And reason for this. So with these examples, let us wind up.